عليكم ورحمة الله وبركاته. بسم الله الرحمن الرحيم. Inshallah, we are starting today the next subsession of neural networks. What we cover in the first subsession is the architecture of the network and also backpropagation algorithm, which is a core step in training neural networks. Okay, so please make sure that you go through the textbook and the handouts that I posted to make sure that you understand how backpropagation works because it is very important. Inshallah, in the remaining part of the session, mainly today, we'll talk about how to train neural networks. Inshallah, if we have time, we'll start to talk about gradient descent and some variants of it. And then we have probably next time to talk about activation functions, regularization, and how we can initialize the weights. And we'll also have a nice demo of using neural networks. Today, the focus will be on training neural networks. Okay, right. For training, what do we need in order to train a network? If we go back to logistic regression, okay, what did we do? What did we need to train the logistic regression classifier? Okay, of course, we need training data, but what else? Huh? These are the model itself that we train, right? We don't need it. This is what we actually learn. But we need also a loss function, right? So we need a loss function. And if we would use gradient descent, of course, we need the loss function and we compute the gradient of it so that we can update the model. So we'll start with the loss function that you saw in logistic regression earlier. This is the loss function. What is the input to that loss function? Of course, this is for a specific one training example. So we compare the predicted value for that example with the actual label. Yi here is the actual label, yi hat is the predicted value, and it's specifically for logistic regression. It was the probability that we predict that the predicted value, the class is yi, is positive. Okay, is don't remember it's y1. Let's say that it's 1. The class is 1. Okay. So in logistic regression, the predicted value is always the probability that the class is 1 given the example. Okay. This loss function, this is exactly what we discussed when we talked about logistic regression. And if you look at it, you'll see that if the predicted probability, the probability of the estimated probability of the correct class is 1, let's say that the true class is 1, okay? So this expression will reduce to this part only, because yi is 1, then this is cancelled. So what we will get is just minus log yi, okay? And because yi is 1, okay, minus log yi hat, which is the predicted probability. If yi is 0, then this one is cancelled, and we will be left with minus log 1 minus y hat. So we can write this loss function this way. We have two branches. When yi is 1, when the true label is 1, then the loss will be minus log y hat. Okay. So if we have a perfect prediction and the perfect probability for that would be 1, right? So in this case, minus log 1 is 0, so we don't have any loss. If the predicted value for the class 1 is, the probability for that is 0, which is the worst case, then this is minus log 0, which is infinity. That's the highest loss we can get. Okay, are you following with me? This is what we already saw in logistic regression. Okay, same here. If the true label is 0, then it will be, the loss will be minus log 1 minus y hat. 1 minus y hat is the probability that the class is 0. Okay, so in case the actual class is 1, it's minus log the probability that the class is 1. In case the two class is 0, it's minus log the probability that the class is 0. Okay, so it's always, we can express it in a different way. We can say it's always minus log the predicted value for the two class. Okay, so it's minus log y1 hat if yi is 1, if the two class is 1, and y hat 0 if the two class is 0. Here we just, instead of using just one value, which is y hat I, we use y hat 1, which is the probability for class 1, and y hat 0, which is the probability for class 0. So all of these loss functions are the same. We are just representing them in a different way. Okay? Any question about this? Again, nothing new here. It's the same loss function that we saw with logistic regression. Is that clear? Because we will build on this. If this is not clear, then please stop me. Fine. Now this is for binary classification. We have two classes only. Can we generalize that to multiple classes? We'll take this last representation and we repeat that for every class. So we'll have something like this. Instead of having just two classes, we have n classes here. So we have n probabilities. One probability per class, and we know that the sum of these probabilities is 1. So the loss will depend on the two class. If the two class is 1, then it will be minus log the probability for that class. If the two class is n, it will be minus log the probability for that class, for the nth class. Okay? So this is just generalization of the loss function, of the cross entropy loss function that we saw in the previous slide. In the previous slide, it was just for two classes. Here, it is for n classes. Okay, and it's the same concept. Type. We can even write this loss function in a more compact way. Again, it's the same loss function, but we can just write it in a simple way to be minus log the probability for the two class. Okay, whatever the two class is. So if the two class is 1, then it will be the probability that the class is 1. If the two class is 5, then it will be the minus log the probability of that the class is 5. Okay. So this is actually the loss function that is used when we have multi-class classification, and this is the cross entropy loss function. Of course, there are other loss functions, but this is the example that we will use for. It's actually commonly used, and this is the example that we will use in neural networks. Any questions? Okay, type. Now we are talking about probabilities, right? In here we are talking about probabilities. All of these predicted values are probabilities, and the whole vector here is just probabilities, right? Type. Do we have probabilities out of the neural network? In general, no. If you remember last time, or I mean last week, when we talked about the layers, we said that the output layer in particular, we don't apply a specific activation function. So the output values of the output layer are actually unbounded. They can be any number. Okay, so they are not probabilities, they are just numbers, any numbers. They can be even negative values. So we will have to have a way to convert these values into values that can be viewed as probabilities. Okay, one common way to do that is using what we call the softmax function. What is the softmax function? We take all the probabilities and we convert them into values between 0 and 1 so that they sum all to 1 using this function. I will explain this function now, and then in the next slide you will see an example that I think will make it more clear. So what is this function? We will take, so here Fi is the output of the network, the weighted sum. Yes. Okay, why are we doing softmax? Okay. You understand up to here, right? Type. This cross entropy loss function is applied on probabilities. It assumes that all of these predicted values are probabilities, and all they sum to 1. Okay, but we are in the context of neural network here, right? The output of a neural network is not a probability. It's just a number. It's a real value. It can be any value. Okay, if we don't apply any activation function at the output layer, which is commonly done, it can be any value. So if we want to apply this loss function on neural networks, we have to convert the values of the output layer to probabilities. And this is one commonly used way to do it, which is the softmax function. So what do we do here? Fi's are the output values. So Fi is the output of the value of the output unit I. Okay, so we'll take every value, we take the exponential of it, so e to the power that value, and then we sum over all the exponentials for all the units. Okay, this way we will get each output will be converted to a number between 0 and 1, and all of them will sum to 1. Type, let's see an example I think will make it more clear. Let's say that this is a network, and we don't care about the structure now of the network. Let's assume that it's either one layer like what you see here or multiple layers. We don't care. We care only here about the output values. So how many nodes we have in the output layer? 3. So this is an example of 3-class classifier. We have 3 classes here. So each node will have a value from the prediction, right? So these are denoted here by the F values. So F1 is the output value for this node, F2 for the second, and so on. And as you see here, the values are not between 0 and 1, and they are not even positive. They can be any value. Okay? Right. Now, given these values, we will apply the softmax function. The softmax function has 2 steps. First, we raise these values with the exponential, with the exponent, with the natural exponent, e, and then if we do that, then we get these values. All of the values will be now non-negative. Okay, they will not be negative at all. Again, these values are not between 0 and 1, right? So still we cannot use them as probabilities. So the second step in the softmax function is to normalize. Normalize means we divide by the sum of them. When we divide by the sum of them, now the values will be between 0 and 1, each value, and the sum of them will be 1. So you see here, these now add to 1, and they can be viewed as probabilities. So again, the 2 steps, we raise it to the exponential, each value. So this value actually is, e to the power minus 2.85. And so on for all of them. Then we normalize. So we take the value that we get from the previous step and divide by the sum of all of them. Okay? This way we get these values. Yes. They are not actual probabilities, but they can be now used as if they are probabilities. Okay? This is, we call this 2 steps, the softmax function. Okay? So the softmax function takes any list of values, any values, and convert them to values between 0 and 1 that sum to 1. Okay? Now we can use these as the predicted values. And now we can use the loss function. Okay? So let's say that now, so these are the predicted values, right? I mean the output values for the network. What should be the predicted class in this case? 2, right? Because 2 is the maximum, right? Right. Let's say that the actual class is 3, not 2. Okay? Then what should be the loss? Minus log which value? The actual value. Okay? The probability for the actual value. Okay? So it will be minus log 0.353, which is 1.04. So that will be the loss in this specific example, if the true label is 3. Okay? Is that clear? So this is now the way how we actually compute the loss for one single training example. Type, let's say that the true label was 2, not 3. The true label was 2. So the predicted class is what? Here is 2, and the true label is 2, right? So what should be the loss? No, the loss is not 0 here. Although the predicted class is the same like the predicted, the actual class, but the loss is minus log the probability for the class. If the probability of the class is perfect, is 1, then the loss will be 0. But because here the probability is not perfect, it's 0.6. So there will be a loss in this case, which is minus log this value. Okay? Is that clear now? Yes. Because that's how we saw the loss function here. So the loss function is minus log the probability of the correct class. Okay, that's how the loss function is defined. Yes. Yes. But y hat I corresponds to the probability of the correct class. Okay. Any other questions? Is that clear how we computed the loss? So what do we need to compute the loss? No, before we apply the softmax function, we have to do something else. The loss depends on what? From the meaning. Forget about machine learning at all. Loss. Okay? So we have to compare two things. We have to compare what we predicted. You cannot actually forget about machine learning, but I mean forget about the specifics here. The loss function is telling us something about the error, right? Of the model. Yes, so we have to know what is predicted from the model and what should be the actual prediction. What should be the true prediction. Okay? So we have to compute two things, or we have to get two things. We have to get the predicted value from the model, and we compare it to the true label. Okay, and this is what we have here. Up to this point, we didn't even have the predicted values because this is just the output of the network. But we have to compare it. We have to convert it to use the cross entropy loss function. We have to convert that to probabilities using the softmax function. Okay, so we have to apply the softmax. With applying softmax, now we have the predicted values. Now we can compute the loss if we know the true label. And of course, in training, we know the true label. So we just compute based on the true label. Here, the true label was 3. So we computed with the minus log of the probability of class 3. Yes. Okay. Regardless of anything in the, okay, so this is the neural network here, right? It can be very deep. Regardless of anything in the neural network, we will just take the output values, apply the softmax. So output values here is the output of the weighted sum only. There's no activation function on the output layer. We just take these values, apply the softmax, compute the loss. We didn't talk about that. Okay, of course that's the short answer, but we didn't talk about how yet. You can guess how, but we didn't discuss it today. Yes. Okay. What was the second question? Okay. The second question was whether we will use this loss in computing the gradients or not. I will answer this inshallah today. Actually, maybe in the next slide, the next few slides. Any other questions? Yes. Yes, Maho. Okay. Type. Do you see this this loss function now? This one. You see this? So the question is, how or where is the relation between the predicted label and the actual label? Okay, in the loss function. Actually, the value that we will get, that will represent the loss, depends on both. How? You see this? There is a branch for each true label. So if the true label, let's say that the true label is 2. Okay. So we'll have to know the true label so that we can apply minus log y hat 2. It's not direct relation like if they are not equal, then the loss will be 1. That's 0, 1 loss. Okay, but cross entropy loss, it's computed that way. It will be computed based on the true label. We look at the probability for that class. Okay, if the probability for that class, which is the true class, is 1, then the loss will be 0, right? Logically. And this is the best we can do, that we predicted the true class with the highest possible probability, which is 1. If you look at this case, it will be minus log 1, which is 0. But if the probability is not 1, then there is some loss. And the loss will not be 0 in that case, even if it is the best value, even if it's the highest probability. Okay, did I answer your question? Any other question? Okay, so this is, as we said, called cross entropy loss. Right. Now, where is training? We computed, we know how to compute the loss, right? How is that used in training? Huh? بالضبط. Exactly. Okay, what we minimize is that loss. We want to minimize the loss function. Okay, we want to find the parameters of the network that will make the loss function minimal. Okay, so we will use gradient descent. Okay, as we did in previous models. Okay, but here we will not just directly use gradient descent. Gradient descent requires that we compute gradient, right? And for neural networks, it is not easy to compute gradient directly. We have to use backpropagation. Okay, so backpropagation will be used to compute the gradients. Actually, I should have written them in the reverse order. Backpropagation plus gradient descent. Okay, because backpropagation will be used to compute the gradients, and then these gradients will be used in to update the parameters using the update rule of the gradient descent. Okay, طيب. Let's dive more in training. طيب. Let's say that now we want to compute backpropagation. Okay. On the previous 2 lectures, we discussed backpropagation in detail, right? What do we need? What are we doing in backpropagation? What is the input to backpropagation? Function. Very good. Now we are in the context of neural network training, right? What is the function? The loss function. Okay, the loss function. So that means that we have to first have the computational graph for the loss function. Okay, once we have the computational graph for the loss function, then we can do the forward pass and then the back propagation pass to compute the gradients, right? So now we need to understand how the computational graph is constructed for a loss function. For any loss function, actually, we just use the cross entropy loss as an example, but the concept is similar. Right. Now let's think together about how to construct the computational graph. Let's say that we have this network. Okay, this is a neural network now. It's not a computational graph. This is a neural network. Let's assume that we have we have an input layer here. So this goes here. Okay, so how many layers we have in this network? 2 layers, right? Okay, so this is the input layer, hidden, and output layer. Okay, now this is a neural network, right? Right. Can we view this as a computational graph by itself? How? Where's the graph here? What is in the computational graph? Steps of computations, right? So we can actually see each node here, each circle here, as a gate in the computational graph. And the gate in a computational graph is doing some computations, right? So what are the computations that we are doing in a neural network? We are doing the weighted sum, followed by, no, the bias is included in the weighted sum, let's assume. And, but after we compute the weighted sum, we apply an activation function at each node, right? You remember that? So if we actually look at, if we zoom in into this node, it's like we compute weighted sum followed by the activation function. Let's call the activation function A. So actually this node can be seen as a gate like this. Okay, you can represent it in 2 gates like this or just 1 gate. Okay, but it has 2 things. It has the weighted sum and it has the activation. And now this net, and of course this is not only this node, it's all the nodes in the hidden layers and the output layer. If we replace now these circles by these gates, then this is a computational graph for computing the output of the network only, right? Do you see this? Any question about this? So this is now, we didn't get to the loss yet. Okay, this is just now converting the neural network into a computational graph for the output values of the network. Okay, so it's very similar. It's almost the same network, but now each node is computation node. Okay, is computing the weighted sum followed by the activation. Any question about this? You have a question, Steve? Do you see this? Okay, type. Now, in order to convert this into a computational graph of the loss function, what is remaining? We have the output already, which is representing what? Before computing the loss, what did we do before that? The softmax function. Okay, so we have to compute the softmax for each output. Okay, don't be misled by the size of the node. Okay, it's just that I need to fit the word softmax, but it's not a bigger thing. Okay, it's just a gate. Okay, so that's the softmax, and then so this is like a layer, but it's actually a layer in computations, but it's not a layer in the network. And in the terminology of a network, it's not a new layer. Okay, it's usually like replacing the activation function for the output layer. Okay, but it's not a new layer. But in terms of computations, it's like a new layer now. Actually, just to be consistent, these nodes now, since we don't apply the activation function on the output layer, It's just the weighted sum. Okay? So all hidden units will be like that, like this one, and the output will be just weighted sum, followed by the softmax, and then followed by the loss, computing the loss. So out of these three values, we will compute the loss. Now this is the function that we want to minimize. Okay, that's the output of the function. Remember in the previous lectures, we have f, which is an expression, and we draw the computation graph for, and we compute the gradients using backpropagation. Now we will use backpropagation to compute the gradients of this specific loss. Type the gradients of this loss with respect to what? Only inputs? The parameters. Where are the parameters here? All the weights and the biases. All of these connections are weights. On every connection there is a weight. It's a parameter. And on every node there is a bias. Okay? So we will have to compute back the gradients of the loss with respect to every single parameter, every single weight, and every single bias. Okay? Using this computational graph. Type, what is needed to actually compute the gradients? Remember in backpropagation we have two steps, right? We have two passes. The forward pass, we compute the output values, so we can compute the whole set of values up to the loss. Then we also compute what? The local derivatives. Okay? What do you mean by the local derivatives? Derivatives of what? Yani for example, local derivative of, for this node. What do you mean by the local derivatives of this node? No, it's not the softmax. So the local derivative at each gate is the derivative of the output of that gate with respect to every input of that. So what are the inputs here? The weights here, right? There is a weight here, there's a weight here, there's a weight here. 4 weights, right? And 4 inputs also, which are the output of that node. But we are only interested in gradients of the parameters. Okay, and the bias, of course, there is a bias here. So the local derivatives are df1 by db, df1 by dw1. If we call this 1, 2, 3, 4, and so on. Okay, and we do that for every gate backward. If you remember last time, we did it, I think, on multiple examples. You do it backward. That's, I mean, you can compute the local derivatives, of course, in forward pass, but then backpropagation, you do it backward. You start from the loss and then to all the parameters of the network. Okay. Of course, you have also to compute with all the output. Although we are only interested in gradients of the weights here, we have to compute also gradient with respect to that output. Let's call مثلا this output is H1. Okay, that's the output of that neuron. We have to compute dl by dh1 because we have to propagate it to the previous layer. Okay, so we have to compute it to all the inputs. The local derivatives are the derivatives of the output of the gate with respect to all the inputs, every single input to that gate, so that we can use it in backpropagation using the chain rule. Okay, is that clear? Any questions? Of course, if you don't remember how backpropagation works, then this is noise. But I believe if you understand how backpropagation works, then this is it should be easy. Okay. Yes. Yes, of course. We said the last time that you can chain gates, you can combine gates. Okay, the only condition for that is that you know the local derivative of the new combined gate. If you know it, then you can combine any set of consecutive gates. Yani you don't have actually to represent this node by these two gates. It can be just one gate, but you have to compute the derivative of the output of that gate now with respect to all the inputs. If you remember last time, we decomposed the sigmoid function into, I think, maybe 3 or 4 gates, but then we said, okay, we don't have to do that because we know the local derivative of the sigmoid, so we can just have one gate for it. Okay, and this is exactly what we do it in implementation, because these are in implementation in the libraries, machine learning libraries. These are just components that you can plug them in. Okay, so every component, it is known the local derivative for it. Okay, and you just need to connect them. Oh, why? No. In the next slide, we don't have this, but you know how to do it, right? And you know how softmax works now. So you can just compute the local derivative for it. What? Log, yes. But in general, this can be replaced by any loss function. The idea that after the computing the output of the network, you add some computations to compute the loss. Okay, whatever the loss function is, you add gates to compute it. Okay, you just need to know how to compute the derivatives for these gates. Okay, the question is, do we need to compute the local derivatives for the softmax? Oh, so what is it? Replaced. Softmax is commonly used, but it's not always the case. There are other ways to do it. Okay, but the concept here is that you replace this part by whatever the way that you will compute the loss with. Okay, type. Let's think about the big picture now. We want to do training, right? So given one example, and one example in classification, of course, we have the feature vector and the label, right? So for one example, we have xi and yi. We already have current model that we want to update, which is represented here by w. So we will do the scoring. Scoring here means we'll do the forward pass. We get the output values of the network. After we get the output value, we get the predicted values. Okay, so this is the whole thing that we saw, most of the picture that we saw in the previous slide. After we get the predicted value, what should we do? We compare it, or we use it with the true label to compute the loss. Actually, the loss that we discussed so far is called data loss, because that's not the whole loss function. If you remember earlier in the course, the loss function has two parts, right? The loss function, the part that is also called the loss, here we call data loss, and another part which is the regularization. Okay, so this is just the data loss. We compute the loss for that example. Then we can also, in parallel, we can also compute the regularization, and then we add them together. Now this is the actual loss function. This is actually the loss function that we need to use in backpropagation. Okay, so what we saw in the previous slide was, if you notice here, what is this? What is this? Without regularization. Okay, without regularization. Okay, if there is regularization, of course you have to add other gates to compute. Okay, and this is what we have here. So now this is the loss, the loss for that example. When we get that loss, now we can apply backpropagation. Okay, when we apply backpropagation, we get the gradients. Then this is just just for one example. right? In the standard gradient descent, we just accumulate these gradients, and we compute the gradient for each training example. We add them. We don't update the model with every example. We update the model after going through all the examples. Okay, why is that? Because actually the actual loss function, because the actual loss function of the model is the average of the loss over all examples. Okay, and this is for all examples. Okay, what you see here in this slide is just for one training example. Okay, we have to repeat that for all examples, accumulating the gradients. Then we do the update for all the parameters. Okay, so this is the big picture for one example. Of course, now after we are done with one example, we go to the next example, and then the third, and then the fourth, until we are done with the entire training data. Then we update the model with all the gradients. This is the standard gradient descent algorithm. Inshallah, in the next lecture, we will see variants of this, variants that are more efficient. Okay, but this is what we call vanilla gradient descent, or the standard gradient descent, that we saw also in Perceptron. Okay, in Perceptron we compute the not Perceptron. When we talked about the linear models, the algorithm that we saw from the textbook, it was using this standard method, which is accumulating the gradients, and then at the end of the entire training set, we do the update once. Okay. Any questions on this? The others are simple also. Don't worry. Any questions on this? Do you understand now how the network is trained? And if we just want to describe it, how do we describe it? The training. How? If someone asked you how your networks are trained, what would you say? Yeah, we compute the loss and try to minimize it, right? How do we minimize the loss? Using gradient descent, okay? But gradient descent for neural networks needs, gradient descent in general needs the way to compute the gradients. For a neural network, it's very complex function, okay? So we cannot just theoretically or manually compute the gradients. We have to do it in an efficient way and systematic way. A way that can be implemented, okay, which is backpropagation. Okay, so backpropagation is a very systematic way of computing the gradients using the chain rule that can be applied to any complex function. Any complex function, if you just draw or represent it using the computational graph, and for each gate, it's very simple to the extent that you know easily how to compute the local derivatives, then backpropagation can compute the gradients for all the parameters. Type once we compute the gradients, we can update the model if we update every example, or we can accumulate the gradients and update the model at the end of the entire training set. Okay. Just as an intro to the next lecture, if we do the update after we see all the training examples, this is, as I said, called vanilla gradient descent. If we do the update after every training example, this is called stochastic gradient descent. Okay, and we'll talk about that inshallah in more detail next lecture. Any questions? See you inshallah next lecture. Assalamu alaikum.